So today I thought that we would continue our conversation on vectors, focusing on the dot product of vectors. Now the dot product of a vector, or the inner product of a vector, has a formula. So if we have two vectors, let's say vector u with components u1 and u2, and vector v with components v1 and v2, we can find the dot product of both of these vectors, u dot v, by multiplying their first components and then adding that to the multiplication of their second components, which would be u1 times v1 plus u2 times v2. Now the dot product of vectors is actually going to be a real number. And this real number is going to have some applications and some uses when we actually try to use vectors in real-world situations. So as you can see, one of our last bullet points is using vectors to find force, which is going to utilize both the dot product of a vector and the projection of a vector. Now let's say we are given two vectors, 3, 4, and we're asked to find the dot product of this vector with vector 5, 2. To find a dot product, one simply has to multiply the 3 times the 5 and then add it to the 4 times the 2. So this would give us 15 plus 8, which would give us 23. And it's as simple as that. That's how you find the dot product of a vector. Now dot products have a lot of different uses. For example, we are going to be able to use them to find the angle between two vectors. So let's say that we have two vectors, and let's actually draw these out. Let's say, for example, that I had vector u with components 2, 3, and I had vector v with components -2, 5. And I was asked to find the angle between both of these vectors, the angle theta. Now there's actually a formula for doing this. Now there's actually a theorem that goes with this, and the theorem is that the cosine of theta is equivalent to the dot product of u times of u dot v divided by the multiplication of the magnitude of both of them. So if we are looking for a formula to find theta, then all we have to do is take the inverse cosine of both sides to get theta is equal to the inverse cosine, or the arc cosine, of u dot v divided by the magnitude of each of these. So let's see how that would work out in practice. First things first, we need to find the dot product. The dot product is going to be 2 times 2 plus 5 times 3. Sorry, that's a -2. So -2 times 2 plus 5 times 3. We get -4 plus 15, which gives us 11. And so -4 plus 15 gives us a dot product of 11. Now to find angle theta, we need to go ahead and find the magnitude of each of these. And we can find magnitude by using Pythagorean theorem or the distance formula. And so we're going to end up with, if we plug our dot product into our formula, theta is equal to the inverse cosine of 11 divided by the magnitude of u times the magnitude of v. Let's see if we can find those. 2 squared plus 3 squared is equal to 13. And if we take the square root of 13, that would give us the magnitude of u. and 2 squared plus 5 squared is equal to 29. And if we take the square root of 29, that would give us the magnitude of v. So we have this divided by the square root of 13 times the square root of 29. So all that's really left to do is to go ahead and plug this into any calculator, as long as we are in, well, whatever we want our angle to be in. In this case, if we want our angle to be in degrees, then we're going to head and make sure that our calculator is in degree mode. So let's look up a calculator. I'll use Wolfram Alpha, and I'm going to be using the arc cosine of 11 divided by the square root of 13 times the square root of 29 making sure that everything is underneath the 11. Once we know that this matches, we get a decimal approximation in radians and a conversion to degrees, which is 55.49. And so using the dot product, we were able to figure out the measurement between. And so using the dot product, we were able to figure out the measurement between these two angles. Now, orthogonal vectors are simply vectors whose dot product is equal to 0. Now, these are going to be useful for us because when the dot product of a vector is equal to 0, then the measurement between the angles is 90 degrees. And we're going to be using this to find projection angles. Now, there is one exception, and that exception is the 0 vector. If you guys remember, the 0 vector has component 0, 0, and so really the 0 vector has a dot product of 0 with every other vector, but it is not perpendicular to every other vector because the 0 vector has no lines, so it can't be perpendicular. So that's the only exception. But other than that, any orthogonal vector is going to have a dot product of 0, and the measurement between the angles is going to be 90 degrees. So that's going to be super important. And now you know what orthogonal vectors are. So let's talk about the projection of a vector onto another vector. Let's imagine for a second that we have vector u and vector v, and we're wanting to project vector u onto vector v. Notice the order that it goes. We're going projector v onto vector u. The formula for this is going to be the dot product of u and v divided by the magnitude of v squared all times vector v. Now, what exactly is projection? Let's imagine for a second that we have a light source, like the sun, and vector u casts a shadow on vector v. The shadow is going to go from the beginning of the meeting point of these two vectors all the way to the point where connecting u and v would form a 90-degree angle. So it's not going to just fall straight down like that and be the exact same length of vector u. It's actually going to be a different length of vector u, and it's going to be a scalar length of vector v. So the question is, what is this vector then? And this formula is what's going to help us to find the component form of this vector. We can call it whatever name we want. We'll call this vector t. Now there's a really great video by a guy on YouTube who has a channel called Firefly Lectures, and so I'm going to go ahead and link you guys to that video because he does a really amazing job at explaining it. But I hope that this sort of gave you a good idea of what vector projection is. Now the way we use it, or the way we would find a problem, or the way we would solve a problem about vector projection, is that they may ask you, okay, let's project this vector onto another vector. So let's say we have vectors, let's say we have a coordinate plane, and let's say I have vector u and vector v. Vector u having component form 6, 2, and vector v having component form 5, -5. Now, if we are trying to project vector u onto vector v, so we're looking to project vector u onto vector v, then the formula for this, again, is going to be the dot product of u and v divided by the magnitude of v squared all times the component form of vector v. So if we were to draw a line between these two, remember it has to be a perfectly perpendicular line with v. So this right here is going to form a perfect 90-degree angle, and what we're gonna be looking for is this vector right here. That is the vector that I'm looking for. That is the projection of u onto v, because it forms a 90-degree angle. All that's left is to go ahead and plug it into my formula. So by using the dot product, 6 times 5 plus 2 times -5, I get 30 plus -10, which is equal to 20. And now I need to find the magnitude of v. That's my dot product. And the magnitude of v is actually 5 squared plus 5 squared is equal to 50. And the square root of 50 is my magnitude, but since we're squaring this again, so that right there is the square root of 50, but then that squared goes ahead and cancels that square root out. I get 50 underneath there. So now my formula, once I plug things in, dot product is 20 divided by 50 all times the component form of v. We can actually go ahead and simplify this into 2/5 times 5, -5. And when we distribute this and multiply it out, just like a scalar multiplication, we actually end up getting, well, this will cancel out, 2, -2. So then the component form of that vector in red is 2, -2. And that would be the projection of u onto v. Now vector projection actually has a lot of real-world applications. And one of them is to find a force required to either stop or start an object that is going up or down a hill. So let's take this for example. Two individuals, one of them is on a sled that is on a hill at 45 degrees. So I imagine that they're playing in the snow and they're on this hill. This guy right here, we'll name this guy Billy and we'll name this guy Bob, is holding Bob so that he doesn't slide all the way down. Now the combined weight of Bob and the sled is 140. So my question is, how many pounds of force is Billy having to use to hold Bob up on this hill? Now you would think, well, if it's 140 pounds that Bob weighs, then that means that Billy could hold him straight up with 140 pounds of force. But he's not having to do that. There is an incline of 45 degrees, so that is actually helping Billy to not have to use 140 pounds of force to hold up Bob. So it's less force. And the question is, how much will that force actually be? And we can find this using vectors, because this angle is going to play a very, very big part in the amount of force that Billy's having to exert. If the hill was steeper, then Billy would have to use more force, and if it was less steep, then Billy would have to use even less force. So to find this out, we're going to go ahead and create a vector. It doesn't matter really in what direction, but we're going to create a vector, and then we're going to project this vector onto that vector to see exactly how much force is going to be required. Let's say we take vectors right here. I'm going to create this vector right here, and I'm going to be looking for this vector right here. Now, the key thing to remember is that the magnitude of this green vector that I drew, or actually let's draw it in blue so we don't confuse ourselves. This blue vector that I drew doesn't really matter. We're making this up. What matters about this vector is the angle. That's where the angle is going to come from. And the reason that the magnitude doesn't matter is because the magnitude, which is going to be the force, so the magnitude is going to be equal to the force needed, is going to come from the red vector, right? So we have vector B, B stands for blue, vector G, which is going to be green. That's gravity. That's gravity working on Billy, and that's 140 pounds. That's the magnitude. And we're going to have vector R, whose magnitude is going to be whatever Billy is having to exert to keep Bob up on that hill. So let's begin by finding out basically the form of vector G right here. So remember, there are a couple ways to write down vector. You have component form, but you also have I and J, which are known as a linear combination of these vectors. So you have a horizontal component and a vertical component. So let's imagine this G as a vector in horizontal and vertical component form. So this has no horizontal form. So what we're going to do is we're just going to say it's going to be 0I plus 140 pounds. But this isn't going up. It's going down. It's working downward. So that's actually going to be negative 140 pounds. So minus 140 pounds J. So this vector G is just going to be negative 140 J. Okay, and so now we have to do the same thing with this blue vector, but we don't have very much information. The only thing that we have is the 45 degrees. So what we're going to do is we're going to be smart, and we're going to say, okay, you know what? I'm going to make this vector B, this blue vector, have a magnitude of 1. Now remember, it doesn't matter what magnitude B has, because red is going to have its own magnitude, which is going to be the force, and that's going to change later anyway. So we can make B have whatever magnitude we want. And to make it easy on ourselves, we're going to make it have a magnitude of 1. That makes it a unit vector. And unit vectors have component form of their magnitude times the cosine of the angle theta times I plus their magnitude times the sine of theta times j. Now the cool thing about this is because it's a unit vector, we can actually get rid of that magnitude because that's just going to be 1. So we have the cosine of 45 degrees times I and the sine of 45 degrees times j. Now if you know your unit circle, you know what the cosine of 45 degrees and the cosine and the sine of 45 degrees are. And the cosine of 45 degrees is square root of 2 over 2, and the sine of 45 degrees is also square root of 2 over 2. So we have square root of 2 over 2i and square root of 2 over 2j. So now we have the measure of both of these vectors. Vector b, the blue vector, is square root of 2 over 2i plus square root of 2 over 2j, and vector g is negative 140j. We can use now our projection, the projection of the formula for projecting a vector onto another vector to find the magnitude of r. And the way we're going to do that is we're going to say, okay, well, I'm trying to project. So now I'm going to use the projection formula to project vector g onto vector b. So b and g. So this is going to mean that I'm going to take the components of this, right, which is going to be, I'm going to take the dot product of g times b divided by the magnitude of b squared all times the component form of b. Now, check out what's going to happen. Well, first of all, the magnitude of b is 1. We made it so that it was 1. So 1 squared is just going to be 1. So really all we need to worry about is this part right here. And if g is 0i minus 140j, then what that means is that the dot product is going to be, well, 0 times anything is just going to cancel out. And then we're going to have this right here. We're going to have to multiply these together. So we're going to end up getting negative 140. And we're not going to be using j's or i's anymore because at this point we're in component form, times the square root of 2 over 2, all divided by 1 squared, which is just 1, so we'll just leave it like that, times the component form of b, which we're just going to leave like this for now. What we're going to do at this point is we're going to go ahead and multiply both of these. And the reason for that is, once again, we're trying to find the dot product. So if I actually multiply this out, I get negative 140 times the square root of 2 divided by 2. So I'm going to get negative 70 times the square root of 2 times the component form of b. And the component form of b, if you guys are going to remember, is cosine of 45 times the sine of 45. Cosine of 45 times the sine of 45. But we actually don't need this, and let me explain why. Because, if you guys will remember, the original formula is the magnitude times the cosine of theta, and the magnitude times the sine of theta. So when I distribute this, I'm gonna go back to this equation. But I don't need to go back because, if you guys are gonna remember, what we're really looking for is the force or the magnitude of r, of my red vector, the one that's here, the one that Billy is using to hold up Bob. So in reality, if I were to distribute this, then I would just be using my magnitude to find my magnitude, which I already have. It's negative 70 times the square root of 2. So Billy is using negative 70 times the square root of 2 pounds to hold up Bob. And if we put this into our calculator, negative 70 times the square root of 2 it's going to give us approximately 99 pounds. Now, since this is magnitude and it is a length, right? Because magnitude is a length, then there is no need for that negative, because magnitude, which is equal to length, always positive. So in reality, the amount of force that Billy is using to hold up Bob is approximately 99 pounds of force. And again, if he were holding him straight up, it would require 140 pounds of force. But in this case, it's only 99 pounds. And so this is one of the easiest ways to show you guys how dot products and how vectors are going to be useful, especially in the world of physics. Because you can imagine how we can just use this for any application that we have when it comes to using force. And I think it's very interesting, and I hope you guys find it interesting. And if you guys have any questions, just please feel free to message me. Thanks.